Good day to all of you. Okay, now this is exactly what we are going to do today. We plan on doing, like I mentioned, independent t-test and one-way ANOVA. So this is manual computation. The reason why we do this is the only way that you can comprehend some of the basic statistical process. So some of you didn't take the class with me in the previous semester. So then some of the concepts could be new, but I will be going through them so that you can brush some of those things up as well. And you will have a very clear understanding of how to reach them by the end of today's session, okay? And before we start, so this is the book that I use, Graviter and Volno 2014, Essentials of Statistics for Behavioral Sciences. I always say you have to get the textbook. If you get the textbook, these concepts are nicely written and you can do your own experimenting with these concepts, do calculations, and at the same time, you can use the software also, and you don't need to limit yourself just to SPSS, because we have done both SPSS, Jamovi, and if I'm not mistaken, we slightly touched upon R software as well. So I think these are little things that you can further focus on. And I think we used another software as well, that is G-Power. G-Power helps us to understand the correct sample size calculations and all of that. So I think overall, pretty good. Overall, pretty good. So let's start the lesson. Now, the first thing that we are going to learn is how to come up with the t-statistic. Now, when you do the independent measures t-test, okay, so here I will be focusing only on independent measures t-test, which means you need to have two separate groups to run this. This is not dependent measures t-test or the repeated measures t-test. Repeated measures t-test is when you have the same group measured twice. For example, before and after a treatment. That is not what we are doing here. This is us trying to understand how to compute the t-statistic if you have two separate groups. So independent measures research. For that, how exactly we are going to find the t-statistic. Now, the first thing you got to do is you have to understand the logic behind running a t-test. Now, why do we run a t-test? Now, the reason to run a t-test is to demonstrate the difference of two groups, and we are proposing the difference should be statistically significant, assuming that there is some treatment that has caused this particular significant difference. Okay, so if you want to focus on the exact reason to run this, so usually you need to have a hypothesis. Now, I always mention in the class that coming up with the correct hypothesis is very important. I noticed even in some of the coursework as well, students have, uh, most of the students have put hypothesis correctly, but some of the students haven't gone through the proper notation, and some haven't really taken the effort to come up with a good hypothesis. Now, for example, if it is a independence t-test, you have to have a hypothesis like this, and you need to come up with the alternative hypothesis. See, in alternative hypothesis, you are proposing or you are predicting. It's a tentative testable prediction. Hypothesis is a tentative testable prediction in which you are saying, okay, look, I have two groups, we are administering a treatment, and if our administration of this treatment is right, assuming this takes place in an experiment with everything else in control, then the treatment would make the two groups differ significantly. So, for example, if you take two groups of students, let's say 30 to two different groups, and you could say, look, we are going to give you all today a different type of movie or something, and then after that we are going to measure your happiness. And one group could receive a normal movie, and the other group could receive a particular type of a movie that the researcher is thinking could make people extremely happy. So if that movie is truly capable of making people extremely happy, then one group should perform better than the other in terms of happiness. So there needs to be a significant difference. So here it says hypothesis one, you can write like this as well. For example, mu1 is not equal to mu2. So sample mean of the first group, that's a sample, right? So that sample mean is different or not equal to the mean of the second group. This is exactly what it says, okay? Now, if you have a hypothesis like this, the next thing that you need to do is to develop your t-statistic. So this is the basic t-statistic. So this is the formula. In the t-statistic, what we do is, it's a very simple calculation. You have to have your sample mean difference, okay? So sample mean difference minus population mean difference, and then you divide it by the estimated standard error. Now, if you write the formula, this is how it would look like. T is equal to M1 minus M2. Now, M represent the sample mean difference, okay? M1 minus M2 minus mu1 minus mu2. Mu1 minus mu2 would represent the population, parameter, so population mean difference. And that is divided by standard error estimate. So standard error estimate, now you can't directly calculate standard error estimate. For this, we had to do a little bit of other calculations as well. But now today we'll be discussing how to come up with this, because this m1 minus m2 and mu1 minus mu2 is very easy to calculate. There's nothing to do over there. But then this would actually take some time for us to figure out, and that is something that we'll be learning today, okay? Now there is that. So in the above formula, M1 minus M2 is obtained from the sample data. Now you have gathered some information about two groups. So that is utilized to understand or come up with the values for M1 minus M2. So that comes from the sample. But mu1 and mu2, this comes from the null hypothesis. So those are the population difference. So in the population, there is no such difference. So we are going to keep it as 0 usually. But in the sample, there's a difference. So that difference we are going to write here. Okay. So estimated standard error. Now for that, you have to start your calculation. Now that is also once again m1 minus m2. What we try to do here is we try to paint a picture about the average distance between the sample statistic and the corresponding parameter population. That is exactly what we try to do in the estimated standard error. So you have the sample difference minus population difference, and then you divide it by the standard estimated standard error. In estimated standard error, what we try to do is we try to find the average distance between sample statistic and the corresponding population parameter. So this entire thing I took from the Graviter and Wallner book. So if you can also take the book, you can take yourself through these analysis as well, okay? So this is the sample difference, M1 minus M2. This is the population difference, mu1 minus mu2. So estimated standard error would try to find the average distance between m1 minus m2 and mu1 minus mu2. So basically finding the difference between sample mean difference and population difference, okay? Now, let's try to develop the formula for estimated standard error. Like I told, the m1 minus m2, there's nothing to come per se. It's pretty much there. We have the data. And then mu1 minus mu2, there's nothing specifically for us to calculate. It's pretty easy, straightforward. But here, estimated standard error, you have to do a bit of calculations. Now, for that, let me take you through the logic, like how exactly we are going to execute this. Now, there are 3 points that you have to consider here. Now, the first one is each of the 2 sample means represent its own population mean, but in each case, there is some error. Now, you have 2 samples. Each sample is representative of their overall population. So both of them have some amount of some amount of error with them. This error cannot be eliminated. Whatever the thing that you would collect, there is some inherent amount of error. So that error is something that you have to account for. So therefore, M1, which is your first group, approximates mu1 because you have one group that represents a specific population. So the mean of this group try to approximate the mean of the population that it represents. So it approximates mu1 but with some error. And then M2 also approximates mu2 but with some error. Thus, there are 2 types of error here. So the second one that you have to do is the amount of error associated with each sample mean is measured by estimated standard error of the mean. Now, so for this, we had to come up with the estimated standard error for each particular group. Now, this is exactly what we do. Now here, M1 and the standard error of that one, it is equal to variance of that group divided by the total number of cases, and then you take the square root. Okay, no? That's the formula that you have to take. So M1 standard error of M1 is equal to variance of that particular group divided by n, and then you take the square root. Okay, no? So this is that particular formula. And you might recall variance is, once again, you have to calculate. Variance have to be calculated through this formula, sum of squares divided by degrees of freedom. But don't worry, now I'll take you through an example. So once we go through the example, it will be clear to you how to calculate variance and all of that as well. So this is estimated standard error of M1. Now, very similar to that, we are going to calculate estimated standard error for M2 as well. Once again, the same formula, but for the group 2. So variance of group 2 divided by the number of cases in that particular group. That's your second step. So for independent measures t-test, we want the total amount of error involved in using 2 samples to approximate the 2 population means. Now you have 2 samples here because you have 2 groups, right? Each group tries to approximate the population mean. And as a result, when you want to find the estimated standard error, what you have to do is you have to combine both of these and try to come up with the combined value so that it can approximate the population means. Now, that is why we write it like this. So the estimated standard error can be written as this. This is the formula. Variance of the first group divided by the number of number of cases in that particular group. Then you close parenthesis, you add again the variance of the second group divided by the number of cases of that particular group. And then once you do the addition, you take the square root for the entire thing. So square root of variance of the first group divided by the number of number of individuals in that group plus the variance of the second group divided by the number of cases in that group. So that's the basic formula here. Okay. So I think it would really benefit if you can follow and do the analysis with me so that you are following each of the steps as well. Okay. So now this is the basic formula. Now, if you have equal sample sizes, this formula is fine. For example, let's say you have two groups, each group has 10 individuals. So 10 in this one, 10 in the other one, that's all right. But when you don't have equal groups, then this particular formula will run into a problem, because then this particular analysis will not give you the correct error estimate. So rather what happens is, the one with the larger number of cases would have a additional weightage here. Okay, so what we have to do in that kind of instances is to go for the pooled variance. Now, only if you have, if you have equal sample sizes, you can still go and do this as well. But if you have unequal sample sizes, as a practice, you can go for pooled variance. And I think this formula is once again pretty easy as well. So pooled variance can be calculated by sum of squares of the first group plus sum of squares of the second group divided by degrees of freedom of the first group plus degrees of freedom of the second group. Okay, now still we are talking about how to calculate estimated standard error. This is our formula, okay? M1 minus M2, mu1 minus mu2. Now, this is very easy to calculate, so we don't have to worry about it. So we are going to keep it aside. We just try to figure this out, how to do this calculation. M1 minus M2, and the difference between M1 minus M2 and the mu1 minus mu2, like the average distance between these two, okay? So we are still there. So this is something that you had to do. You had to go for pooled variance. Pooled variance in the sense, so here in this example, pooled variance can be calculated like this. Let me quickly take you through. Now, estimated standard error, this is the formula, the one that we were discussing. This is the formula. Now, here you have normal variance. If you have unequal sample sizes, instead of the normal variance, what you do is you come up with this pool variance. Okay, I think my previous explanation was slightly confusing. I told that instead of this, you can go for this. So what happens is, this is your standard error, standard estimate of error formula. And as you see here, this is variance divided by the number of individuals in the group. But if you have unequal sample sizes, in that situation, instead of the variance of that group, you would be substituting, or you would be using the pooled variance. So pool variance have to be calculated through this formula, that is sum of squares of the group 1 plus sum of squares of group 2 divided by degrees of freedom of group 1 plus degrees of freedom in group 2. Okay, so this is the formula. This is the basic formula. So if you go to your previous example, I'll take it here. Well, I take this and copy it to the main formula that we have earlier. Give me a second. Now, this is exactly what is happening. I'm going to color it in a different color. Okay, this is exactly what we'd have to do. So T statistic is calculated by M1 minus M2 minus mu1 minus mu2 divided by estimated standard error. Now, estimated standard error can be calculated by taking the square root of variance of that group divided by the number of cases plus variance of the second group divided by the number of cases. But if the sample has if the two groups are unequal, which means one group has, let's say, 8 and the other group has 10, then these are unequal sample sizes. In that case, you would have to take the pooled variance. So let me take that as well. So in that case, you might have to get pooled variance. So I'm going to just color and keep it over there as well. In that case, here's what you have to do first. I'm going to simplify this. This is your formula. Let's say you have two groups with two unequal sample sizes. The first thing that you need to do is, these values are easily available, we'll go through it. So the first thing you need to do is to calculate the pooled variance. Sum of squares of the first group plus sum of squares of the second group divided by degrees of freedom of the first group plus degrees of freedom in the second group. You have then the sum of the pool variance value. So once you have the pool variance, then in that, instead of this formula, you can actually go for a formula like this, where you actually utilize, give me a second, this, okay. Let me take that and copy and paste here as well. So if you go for pool variance, it will slightly change your formula like this. Okay, no? This is the usual formula to find your standard error estimate. But when you don't have equal samples, you have to go for pooled variance. And once you have pooled variance, your pooled variance would come here instead of the usual variance of the group. So that value here is going to be the same for both the groups. Pooled variance is a common variance for both the groups. Okay. So that pooled variance will come here and here. Now here, these are two different variances. So variance of first group and variance of the second group. You eliminate those and include the pooled variance value. So this is basically your entire calculation. Now, we'll just go and try to understand why exactly we need to have pooled variance, okay? Now, here there's a sample study with equal sample sizes. Now, here you have your first group, 6 individuals, and here we have sum of square value of 50. Here you have your second group with 6 individuals with sum of square value of 30. Now here you have same sample size, but sum of squares, of course, that could change depending on the score each one has scored. Now, these are equal sample sizes. Now here the first thing is you have to calculate the t-statistic, you have to have variance. So now let's calculate the variance of our first group. Variance of the first group can be calculated by sum of squares divided by degrees of freedom. So sum of squares of the first group is 50. Degrees of freedom is calculated for a particular group by n minus 1. Okay, so let me write it here. Degrees of freedom is n minus 1. That is clear. So let me quickly format it. Okay. This is the degrees of freedom formula. I'm going to just keep it here. So degrees of freedom is n minus 1. So that is then you have 6 people. So degrees of freedom is 5. So 50 divided by 5 is 10. And variance for the second group, again, sum of squares of the second group divided by degrees of freedom. Sum of squares is 30. And then degrees of freedom is going to be 5 again because same, sample size. So 30 divided by 5 is 6. So here the total variance, if you get the pooled variance for both of these groups here would be 8, like the direct midpoint, because see, 50 plus 30 divided by 5 plus 5, that is 80, divided by 10, that is 8. So the value would always be between 10 and 6, right at the middle, because both the samples have equal sample sizes. Okay, that is just how it works. The variance is 10 for one group, 6 for one group, so your pool variance would be the midpoint. However, when you have unequal sample sizes, it's going to be slightly different. Now here you have one group with 3 individuals, sum of squares 40. Second one has 9 individuals, sum of squares 48. So the variance for the first group is sum of squares divided by degrees of freedom of that group, that is 20 minus 2. 2 has been derived by n minus 1, so n is 3 minus 1, that becomes 2. 20 divided by 2 is 10. So then variance for the second group, sum of squares of the second group divided by degrees of freedom of that group. So 48 minus 8, 8 has been derived by n minus 1, so 9 minus 1, that is 8. So that is, the answer is 6. Now here, the pooled variance is not going to be 8. Why? It cannot be 8 because one sample has more individuals. So here the pooled variance is when you calculate, now this is what you have to do when you have unequal sample sizes. Sum of squares of the first group plus sum of squares of the second group divided by degrees of freedom of the first group and degrees of freedom of the second group. So 20 plus 48 divided by 2 plus 8, that is 68 divided by 10. So the answer is 6.8. So the resulting value is closer to the values of the second group because the second group has a larger sample. So when computing the pooled variance, the weight for each of the individual sample variance is determined by its degrees of freedom. So because the larger sample has a larger degrees of freedom value, it carries more weight when averaging the two variances. So that's the basic idea. So the second group has a larger degrees of freedom, that is 8. So as a result, it tends to carry more weight. Okay. So that is exactly what happens here in this pool variance. Now, when you have that, you can go ahead and do your t-statistic calculation. Now, here's another alternative formula to compute pooled variance. Degrees of freedom times the variance of the group plus degrees of freedom times the variance of the next group divided by degrees of freedom of the first group plus the degrees of freedom of the second group. Now, there is no reason for us to go for that because we can easily do the calculation with the formula that we have been doing. So estimated standard error, this is the formula. Square root of pool variance of group 1 and group 2 divided by, so pool variance is of course the same value for both the groups, so square root of pool variance divided by number of cases of the first group plus pooled variance divided by the number of cases of the second group. Okay, and this is exactly what we have discussed so far. So this is your calculation. Okay, unequal sample sizes, you can just go with this. So the equal sample sizes, you can go with this. So just directly you can go for that. But if you have unequal sample sizes, go for pooled variance, and then this is your formula for standard estimated standard error. Okay, no? Right. Now, these are the things that we have discussed. These are your calculations. First, you have to get the sample data M1 minus M2. Then the population parameter mu1 minus mu2. Pooled variance is sum of squares of the first group plus sum of squares of the second group divided by degrees of freedom of the first group plus degrees of freedom of the second group. And then you have a standard error estimate. Standard error estimate is the pooled variance of the two groups divided by the number of cases of the first group plus pooled variance divided by the number of cases of the second group, and for the overall thing you get a square root. Now these are all your calculations. Now let's do a sample exercise to understand how to go ahead and compute your t statistic. Okay, now here we have some sample data. TV viewing habits of 5-year-olds and future high school performance. So very easy study. We have one group of students, kids who have watched Sesame Street, and we have another group of students who have not watched Sesame Street. And this is their high school performance. Okay. Now, we have 10 cases in each group. So 1, 2, 3, 4, 5. So 10 cases for each group. There's 10 students who have watched Sesame Street and 10 students who have not watched Sesame Street. Now the mean of the group that has watched where they have watched Sesame Street is 93, and the mean of the group where they haven't watched Sesame Street is 85. Now there's obviously a very noticeable difference here. There's a difference of 8 points between the means, but we have to test whether this mean is statistically significant or not. Now here we have a sum of squares of 200, here we have sum of squares of 60. But before we go through the statistic calculation, let's try to see how exactly we are going to calculate sum of squares and all these kind of things. Now this is your data. This is what you have to do. This is the first table that you have to compute. So this x values indicate the values or the scores of the students who have watched Sesame Street. Now see 86, 87, 91. So I have the same thing here. So I have listed them here. So some students, actually some individuals put this in alphabetical order. Doesn't matter. I mean, it still gives you the same calculation. So you can just put the data here and you can calculate the mean here. So the mean is 93. Okay, pretty easy. Now that is your x, which means the values of your group 1. And I have represented values of my group 2, that's the group where they haven't watched Sesame Street, by y. So the values start from 90, 89, 82. So the same thing I have listed, and they have their mean 85. So M1 is the mean of the first group. Okay, no? Mean 1 means, this is the first group. So M1 represents the mean of the first group. That's 93. M2 represents the mean of the group 2, that is 85. So I already have some components of my t statistic with me now. M1 and M2 now I know. And mu1 and mu2 is always 0. That also we know now, because that's the population parameter. In the population, there is no such difference. That's why in our sample, we are going to show a difference, okay? Because the hypothesis is to show that group 1 is different from group 2, no? So mu1 and mu2, always the null hypothesis would say there is no difference. So because m1 minus m2 comes from the sample, mu1 minus mu2 comes from the population. So mu1 and mu2 in the population for the null hypothesis, like I told, it comes from the null hypothesis. So that there you don't have any specific differences. So that's always going to be 0. We'll get to that. But let's focus on this set of calculations. So the first thing that you have to do is, now this is your data for the first group. Go for this x minus x bar. That's the thing that you have to do. So x represent each data point here, each score here. X bar represents the mean. So deduct 93 from 86. The value is going to be negative 7. Deduct 93 from 87. The value is going to be negative 6. Deduct 93 from 91, the value is going to be negative 2. Deduct 93 from 97, the value is going to be plus 4. Deduct 93 from 98, that's 5. 93 from 99, that is 6. 93 from 97, that is 4. 93 from 94, that is 1. Again, 93 from 89, negative 4. 93 from 92, negative 1. Now, if you calculate all of this, the answer should always be 0. Then you know your calculation is right, okay? So sigma means the combination of everything. So sigma x minus x bar should be equivalent to a 0. Now that is your first step. Now what you have to do is x minus x bar, then you square this value, okay? No? So see, x minus x bar squared. Now x minus x bar for the first score here is minus 7. So minus 7 times minus 7 is plus 49. Minus 6 times minus 6 is 36. Minus 2 times minus 2 is 4. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 4 times 4 is again 16. 1 times 1 is 1. Negative 4 times negative 4 is 16. 1 time, negative 1 time, negative 1 is positive 1. Now, sigma x minus x squared. So if you calculate all of these, then you get sum of squares. So the combined value of all of these comes for a 200. So that is your sum of squares. Okay. Now we have calculated, now we have the m of that first group and then sum of squares of that group as well. Now, degrees of freedom also you can very easily calculate for this group because the degrees of freedom is going to be n minus 1. For the group, n minus 1 would be 9 because here we have 10 cases. So 10 minus 1 is going to be 9. Okay. Now let's go for y. Once again, you do the same process. Y minus y bar. So 85. Reduce 85 by 90, that is plus 5. 85 by 89 plus 4. 85, sorry, 82 by 85. So that is going to be minus 3. So reduce once again 85 from 83, that is going to be negative 2. So 85 minus 85 is 0. 79 minus 85 is negative 6. 83 minus 85 is negative 2. 86 minus 85 is plus 1. 81 minus 85 is once again negative 4. 92 minus 85 is plus 7. So sigma y minus y bar is equal to once again 0. And then you take the y minus y bar squared value. So 5 times 5 is 25. 4 times 4 is 16. 3 times 3 is 9. 2 times 2 is 4. 0 times 0 is 0. 6 times 6 is 36. 2 times 2 is 4. 1 times 1 is 1. 4 times 4 is 16. 7 times 7 is 49. So you combine all of this. So the sigma of y minus y bar squared, that's going to be 160. Now you have the sum of squares were 160. Now the next thing that you have to do is to come up with your hypothesis. So this is your null hypothesis. Null hypothesis is always, null hypothesis will always say the two groups are equal. And our alternative hypothesis will say no, this is going to be different. There's noticeable statistically significant differences. So we are demonstrating this. We are trying to demonstrate this. So for that, the first thing is we have to come up with the alpha value. Usual alpha value is 0.05. But here in this example, in the book by Graviter and Volno, they have selected alpha value of 0.01. So 0.01 means it leaves us with the confidence interval of 99%. Now, when you have this alpha, the next thing that you need to do is to calculate the degrees of freedom, not for one group. Degrees of freedom for one group is required when we do those calculations, but here to determine the critical region for the t-test, you have to get the overall degrees of freedom. So df, degrees of freedom of group 1 plus degrees of freedom of group 2, that is n1 minus 1 plus n2 minus 1. So the degrees of freedom of first group is 9, the degrees of freedom of the second group is 9, and that is overall equivalent to 18. Now let's go to the T table. You have to find something called the critical region. Critical region. So this critical region have to be spotted from the T distribution. Now why do I have to do this? Because when you calculate the T statistic, the resulting T statistic should fall beyond this critical point for you to confirm that your test is statistically significant. So what I'm going to do is I'm going to go to the T distribution. Now we have taken here on the top line you have one tail tests, and here you have two tail tests. I am going to go for the two tailed 0.01 because that's our what do you call alpha, and our degree. So this is our first column. So for this we have to find our degrees of freedom, that is 18. Here you have 18 of degrees of freedom. For degrees of freedom of 18 with an alpha of 0.01, the critical region is represented by 2.878. 2.878. So this is clear, no? Two tails, 0.01 alpha, 18 degrees of freedom, the critical region is 2.878. So from the T distribution for degrees of freedom 18 and alpha 0.01, the critical regions are T plus 2.878 or minus 2.878. It's a distribution, you have both plus and minus. Okay, no? So now what you have to do is you have to do this calculation, and you will get a value from this, and that value should be more than plus or minus 2.878. If it is the case, then your groups are statistically, the differences are statistically significant. Now let's go ahead and do the calculation. Now, the first thing that we have to do, now we know the m value, so there is nothing to calculate over there. We know mu values as well. So the first thing that we have to do is immediately start with pooled variance. Now, I know we have equal sample sizes, but that's okay. You can go ahead and calculate pool variance because the variances of the you will get the variances of both the groups separately as well. If you want to calculate variance, you can calculate from here. Just sum of squares divided by degrees of freedom, you will get the variance here. And then if you get the pool variance, it would be between the variances, the two variances of the two groups. So let's first calculate the pool variance. So sum of squares of group 1 plus sum of squares of group 2 divided by degrees of freedom of group 1 plus degrees of freedom of group 2. Sum of squares for the first group is 200, is here. Sum of squares for the second group is 160. So 200 plus 106 divided by 9 plus 9. So each group had 10 individuals. So degrees of freedom is n minus 1, that is 9. So 9 plus 9 is 18. So 360 divided by 18, the answer is 20. So pooled variance is 20. Now let's compute the estimated standard error. Estimated standard error is the square root of pool variance divided by sample 1 plus pool variance divided by sample 2, that is 20 divided by 10 plus 20 divided by 10, and then you take the square root. So that is the square root of 4. So the answer is 2. So standard error estimate is 2. Now let's go ahead and calculate our t statistic. m1 minus m2 minus mu1 minus mu2 divided by the estimated standard error. Estimated standard error now we have, that is 2. So m1 is 93. Let's go to the calculation. This is m1 93, m2 is 85. So 93 minus 85 minus mu1 minus mu2, that is always 0, divided by 2. 2 is the estimated standard error. That is, so the answer is 8 divided by 2, and the final answer is 4. Now, since the t value here is 4.0, this 4.0 is beyond the threshold of the t that we got from the distribution for alpha 0.01 and degrees of freedom 18. The value that we got was plus 2.878, and the obtained t statistic here is 4. So since 4 is greater than 2.878, we reject the null hypothesis and then we accept our alternative hypothesis. So voila, this is exactly what you have to do in independent samples t-test. Now, this is a very clear method of doing uh, independent measures t-test. So this is the basic formula that you have to follow. Now, just to make it more interesting, I also included the Cohen's d calculation. So you know Cohen's d is a method to find the effect size. Now, effect size can be calculated like this: m1 minus m2 divided by the square root of the pooled variance. So 93 minus 85, and then pooled variance is 20, so the square root of 20. So that is 8 divided by 4.7. The resulting answer is 1.79. So 1.79 is a very large effect size. And very similar to that, you can also calculate R squared, which will help you to explain the variability in high school grades explained by the treatment conditions. So that can be assessed through R squared. So R squared is actually t squared divided by t squared plus degrees of freedom. So t squared is 4 squared. So 4 squared divided by 4 squared plus 18 is 16 divided by 34, and that is 0.47. So 47%. So high school grades can be, the variability of high school grades can be explained by the Sesame Street by to a 47% based on what we are seeing here. Now, I know that technically speaking, that can't be the reason. I don't think Sesame Street would account for that much of variability in something like that. But this is just us trying to understand, because high school grades would be determined by quite a lot of factors. And also, in a true experimental sense, it would be very difficult for us to demonstrate something like this, because Sesame Street students have got some time back. So we can't necessarily say it is only the Sesame Street. So because the student who watched Sesame Street may have watched a few other programs as well. So, but you understand how the calculation works. So the critiquing the calculations, critiquing how exactly we have done this, that is something we can do. Now, that is what we had to do in methods as well. Now, in a situation like this, ideally you should consider how exactly this method is applied in a scenario like this. Now, the calculation is easy, but what we have to do is we have to go ahead and find whether this kind of what do you call, now, even though the analysis is clear, you have to see whether the study design is accurate or not, whether this study design gives you a proper picture about causation. So these kind of things also you should be able to critique. Now the study is about watching Sesame Street and high school performance. So is this a true experiment? Because those who have watched Sesame Street and have not watched Sesame Street, uh, I don't think you can directly manipulate that particular variable because there is no random assignment over there, and random assignment is a key ingredient for a proper experiment that will test causation. Now here, since we don't have that, we know the groups are significantly different, but we don't know for sure whether it is the Sesame Street or not. But based on the data that we have here, Sesame Street do have a pretty big impact on these students' performance. But my argument is maybe the students who have watched Sesame Street may have watched other stuff as well, because we don't have significant controls here because there is not an experiment. So this is your final, what do you call, the interpretation. T within brackets you write degrees of freedom 18 is equal to 4.00, that is your T value, and then your P value, uh, and then your coherence D value. Now this is how you run a t-test. So since we calculated the coherence D here, let me put this value also on our first page itself so that you would know that this is another calculation that you would have to. This is not compulsory, but if you do calculate this, it would make your research results really awesome. So this is like a third step that you can do. So pretty nice. Now this is how you would calculate a t-test. Now I know sometimes when you go through this for the first time, it might be slightly overwhelming. But then again, the purpose of doing this is to not to test you or the students for their capacity to do manual calculations. But what we try to do here is, since we mostly run software assisted calculations, I decided the students should also have some good understanding about how these concepts are formed. If you don't have that understanding, the difficulty comes not today, but in your postgraduate studies. Because in postgraduate studies, you have to critique how good this analysis is, why there is these kind of things. And sometimes when you create bigger models like structural equation models and all of that, you have to have a better grip on what is variance, what is covariance, what is variability. You do things like fact analysis, so you need to have some understanding about all of this. When you don't have the basic understanding, you might run analysis, you might be able to interpret the analysis as well, but it will be very difficult for you to know what exactly is happening in the rest of the data. So that is exactly why I decided that we need to do this. Now, this is how you would do a T statistic for independent measures research. So pretty cool. Okay, now with that, I'm going to take you through ANOVA. Now here, similarly, we are going to do one-way ANOVA as well. Now, I'm not going to do two-way ANOVA because that's a bit more complicated, but we can do one-way ANOVA. So first I will introduce you some important notation and formula. Now the first one right here is K. K represents the number of treatment conditions or number of levels in a factor. Okay, that is K. And then simple N represents number of scores in a treatment. Capital N represents total number of scores in the study. Sigma X represents sum of all the scores. T represents treatment condition. And G represents sum of all scores in the research study. We call it the grand total. So G is equal to sigma T. Okay. So these are some of the basic notation and formula that we would require. Now with that, let's go through a sample ANOVA. Now, here we have three groups, once again equal sample sizes. Uh, Here we have our treatment 1 group, treatment 2 group, treatment 3 group. So the research is about different telephone conditions. So I haven't specified the specific dependent variable here, but you can think of something that suits. So treatment 1 is no phone condition, treatment 2 is handheld phone condition, treatment 3 is hands-free phone condition. And these are our values. Now, very similar to what we did in the T table here, the first job you got to do is to calculate the sum of squares. So if you do sum of square calculation manually, first you need to have a table like this so that you could come up with the sum of squares and all of that as well. But let's just assume for the example that we already have done it, and let's just straight get to the values. Now, treatment 1, so T1 has a score of 20. So this 20 has been derived like this. 4 plus 3 is 7. 7 plus 6 is 13. 13 plus 3 is 16. 16 plus 4 is 20. So T1 is 20. So 20, so the T1 is 20. Here T2 is 5. So 1 plus 3 plus 1 is 5. T3 is 1 plus 2 plus 2, that is once again 5. So sum of squares for the first group is 6. Now you know how to calculate this. Let's say this is x minus x bar. You do it for the values, right? And then you take the, then you square them, and then you take the overall calculation of those squared values. So that will altogether come to a 6. So sum of squares of group 2 is also 6, and sum of squares of group 3 is 4. Now, what is our n? Simple n represents the number of cases in the treatment group. So n is 5 for all the 3 groups, and m is the average. M1 is 4, M2 is 1, M3 is 1. So sigma x2 is 106. Okay, so how do we calculate this? We calculate it like this. So x squared, that is 4 times 4 is 16, 3 times 3 is 9, 6 times 6 is 36, 3 times 3 is 9, 4 times 4 is 16, 1 times 1 is 1, 3 times 3 is 9, 1 times 1 is 1, 1 times 1 is 1, 2 times 2 is 4, 2 times 2 is 4. You calculate all of that, you get sigma x squared, that is 106. That is a value that you need to have when you do one-way ANOVA. And then G, the grand total is 30. So 4 and 3 is 7. 7 and 6 is 13. So that is 20. Here 5, 5. So that is the grand total of treatment conditions altogether. That's a 30. Capital N, that's the number of cases you have in the entire study. That is 15. And number of treatments, so levels in the factor. Because telephone condition is our factor, it has 3 levels. So K is 3. Okay, no? I hope these values are all clear to you. Okay, so this is exactly how we go ahead and come up with these. Now, once you have this particular table, the next one is to come up with the ANOVA formula. Now, this is your basic ANOVA formula. It is represented by F. We go for F ratio. F is equal to variance between the treatments divided by variance within the treatments. This is how we understand this is how we calculate the ANOVA statistic, ANOVA ratio. So variance between the treatment divided by variance within treatments. So each of the two variances in the F ratio is once again calculated using the basic formula for sample variance. So sample variance, like we know, can be calculated by sum of squares divided by degrees of freedom. Now here, for you to run the ANOVA, you need 9 calculations. So there are 3 values for calculating sum of, there's 3 values that you have to calculate for sum of squares. 3 different sum of square values. I'll take you through it. And then there's three values you had to calculate for degrees of freedom, three separate degrees of freedom values. Like always, there's a total value, there's a between value, there's a within value for both sum of squares and degrees of freedom. And very similar that you had to calculate two variance values and then final F ratio value. Okay. Now that is exactly what we have to do. So let's go through our calculation. So this is the full set of calculations. Now I included this to give you an idea about what exactly happens. So I know I could have put this in different pages, but I didn't do it because I think if I do it like that, then it will become very difficult for you to follow like what exactly is happening. So I put sum of square calculations on the left. So this portion is also sum of square calculations, degrees of freedom calculations here, and then F statistic calculation here. Now, let's do this. Now, here's what you got to do. First, calculate total sum of squares and then partition this value into two components, between treatments and within treatments. This is the first thing that you need to do. Okay, no? You have to first calculate the total sum of squares. Now let's calculate the total sum of squares. That is, total sum of squares have to be calculated by sigma x squared minus sigma x squared over n. Now here, sigma x squared, we know that is 106. How do I know it? Because we calculated that is 106. So 106 divided by 30 squared. Okay, now notice the difference. Here that is sigma x squared. Here sigma x n squared of sigma x. So here sigma x squared, this one is 106. This one is 30 times. So sigma x means the total scope. Here sigma x squared is 106, but this is actually the grand total we are talking about, that is G. So here I think the ideal thing to do is to substitute this with the G. Then your formula is going to be correct, so that it will comply with the ANOVA notation. So I have mentioned it here. So sum of squares total, that calculation is sigma x squared minus G squared over n. So that is 106 minus 30 squared divided by 15. Now that answer is 106 minus 60. So the answer is 46. That is your sum of squares total. Now once you have sum of squares total, you have to come up with the sum of squares for between treatments and within treatments. So sum of squares for within treatment is the sigma of sum of squares. So sum of squares for each group we have here. For the first group, sum of squares is 6. For the second group, sum of squares is 6. And then for the third group, sum of squares is 4. So 6 plus 4 is 16. So that is your SS within treatment value, that is 16. And then you have SS between treatment, that is sum of squares for between treatments. So sum of squares for between treatments is sum of squares total minus sum of squares within. That is, you can write it like this: sigma t squared minus n minus g squared minus n. So basically what happens is, so here we have to calculate the SS total, okay, and SS total is, SS total, and here for this you have to actually substitute this t squared. Let's check t squared. Okay, so we haven't come up with the t squared here, but let's come up with that. So here's the basic calculation: sigma t squared minus n. So we know the treatment calculation, here's what happens. So for the first one, we have t value that is 20. This is the t value that is 20. So 20 times 20, so 20 squared divided by 5, that is the n. That's the first group. And then second group, you have t, that is 5, so 5 square divided by 5 and 5 square divided by 5. So because you need to have the sigma of all of that, okay. So this is us calculating the sum of squares between, okay. So sum of squares between is calculated like this. Now divided by the total g minus n, that is 30 squared divided by 15. So the answer is 80 plus 5 plus 5 minus 60, that is 90 minus 60. Overall answer is 30. Now here, give me a second. Okay, yeah. So this is exactly how you would calculate that SS between. So SS between is SS total minus SS within, but you will notice that this total doesn't correspond with this total. Now there is something I would have to figure out. I'll put up a remark about that later. But yeah, so as long as we follow this particular method, we are all good. And you can also check this against the textbook as well, why exactly we have a different score here. The reason why we have a different score is because here the formula is different. Here, although we have calculated SS total, here we go for sigma x squared. Uh, but here this is sigma t squared. So that's the main difference that you have here, okay? So we need to have all these values. That's the thing that you have to remember. Now then, we'll start with the analysis for degrees of freedom. Now here's what we try to do. Once again, you have to come up with the degrees of freedom total, that is n minus 1. N minus 1 means, so capital N minus 1, capital N is 15, the total number of cases in the study. 15 minus 1, that is 14. Okay, no? And then you have within treatments degrees of freedom, that is sigma n minus 1. So you have three groups n minus 1. So here remember, simple n stands for sample of each group minus 1. So 5 minus 1 is 4. So sigma of all the 4s, because you have three groups, that is going to be 12. So 15 minus 3 is 12. And then you have between treatments degrees of freedom. Between treatments degrees of freedom, that is k minus 1. How many treatment conditions you have? 2. 3. So 3 minus 1 is 2. That is k minus 1. Now, since you have all of these values, you can go ahead with the F statistic calculation. So F statistic calculation can be calculated like this. So we write it as calculation of variances. So MS variance is equal to the variance. So that is sum of squares divided by degrees of freedom, which is, so that's the MS variance. And then you have MS between variance. So that is represented as variance between. So that is equal to sum of squares uh, between divided by degrees of freedom between. So sum of squares between, let's try to find that value here. Sum of squares between value here we have, that is 30. So 30 divided by degrees of freedom between, that is 2. 30 divided by 2 is 15. Okay, no? So I'm going to color this in a different color. Okay. So sum of squares, variance within, that is sum of squares within divided by degrees of freedom within. So sum of squares within, that is 16. So we need this value as well. So I'm going to color this as well. Whatever the values that we need, I'm going to color them here. Okay, we took this one as well. And now we need this is the within treatment value. 16 divided by, once again, degrees of freedom within. Within value is actually 12. I have written it as 2, which has to be 12. So that is here. We have 12. And the resulting answer is, so 16 divided by 2 is 1.33. Now we have that value as well. Okay. So now we can calculate the final F-score, that is variance between divided by variance within. Variance between is 15, variance within is 1.33, and the resulting answer is going to be 11.28. That is your F-score. Now, if you want to test the hypothesis, what you can do is you can actually find the critical point from the F table. Now let's keep alpha at 0.05 and try to locate. Now here's the F table. Now here you have the numerator degrees of freedom. Numerator degrees of freedom means the between treatment df. The denominator degrees of freedom is the within treatment df. So our values are 2 and 12. Now let's find that. Here we have degrees freedom, here we have 2, and the other one is 12. Here, right here, alpha anyways here for the entire table is given at 0.01, so that's all right. So our critical region is 12.9266. 6.9266. 6.9266. So let me write that. Critical region is plus 6 point, oh I forgot that already, 6.9266. 6.9266. Now here's what you have to now think. This is the critical region. So in critical region, what happens is, if the value that you have is beyond this critical region, so then you have to reject your null hypothesis and accept the alternative hypothesis. So here the critical value is 6.926 and our F ratio score is 11.28. So 11.28 is significantly away from plus 6.92. So you have to accept the alternative hypothesis. Okay. So alternative hypothesis would also say that there are significant differences between three groups. T-test would say between two groups. This would say between three groups. Now this is your final output table. Between treatments, your sum of squares is 30. We already have that from this table. Okay. Not that table, from this table. Here. And then degrees of freedom for between is 2. How do I know? It's right here. And then the variance for between is 15. It's here. And then within treatment, sum of squares is 16. Value is here. And then degrees of freedom is 12. Variance is 1.33. We calculated all of this in the previous slide. And then the total is 46 here. sum of squares, and then degrees of freedom total is 14, and then the resulting F score is 11.28. So here's the interpretation. F score is between treatments, that is 2 degrees of freedom, comma 12 within treatments equal to 11.28, and this is statistically significant. So what it means is we had 3 groups: treatment 1 no phone condition, hand phone condition, handheld condition, and then hand free condition. These are all the statistically significant differences. So this ANOVA is statistically significant. Now, this is what I wanted to discuss today.